Hello all, welcome to the episode 16 in this Deep Learning with Pytorch series. So far we have looked into how to train a neural network model only using a trained data set, right? So slowly we will introduce the other type of data set like test and validation. And in this video, we will talk about how to choose your neural network parameters, what is bias and variance trade-off, what is overfitting and underfitting, and how you can also tackle that. So this would be a very interesting video. So I would request you to stay till the end of this video and watch it completely because this is very essential for you to know these concepts if you want to work in the deep learning side, right? So let's get started. So first of all, let's discuss how to choose neural network parameters, right? So far you have seen that we are building a neural network with certain number of hidden layers, certain number of nodes in each of the hidden layers. We also choose different parameters of the neural network, right? So you might already have these questions like how we will choose the number of layers, how we will choose the number of nodes in each layer, then what would be the activation functions, what would be my learning rate, right? And a few other things like how many epochs should I run, right? Then what would be the batch size, what is a optimal optimizer for training my neural network model, right? So all this is the questions you might be having at this point, right? So to disappoint you that there is no straightaway answer for these questions. So what you need to do is you come up with an idea, you do certain experiment, you write the code using those parameters of your neural network model, and then you measure the performance of the model, right? And then you see how the model performance is by using those certain parameters, and based on that you take decisions, right? Whether we need to go ahead with that particular specific parameters, or we need to go ahead with different type of parameters, right? And so this is kind of experimentation work, and that is one of the reason we call this data science, right? Because we work with a lot of experiments and we need to do a lot of experimentation to come up with a specific set of parameter values, right? Now, how do we choose these parameters? Do we only choose looking at the training set performance, or there are other things we should consider, right? So let's go ahead and try to understand like where we should check the model performance, right? So generally, in case of machine learning or in case of deep learning, we generally divide our full data set in three sections, and that's we call as train, validation, and test set. So you have the full data set. So this is my full data set where like the 70% of the data is like generally it is training data set where the model is getting trained, and using validation data set we kind of fine tune our model and we try to find out the best parameters for my model, which the questions which we trying to answer, right? So that we generally try to use see the performance of particular set of parameters and see how the model is performing on that validation set, right? And once you kind of see that the results are quite optimal, and then you go ahead and check on a test set. So this test set is a completely unseen data. So in case of validation, still your model is kind of looking into a validation set, and based on that you are fine tuning the model hyperparameters, right? But test should be completely unseen, and you will not do any fine tuning based on the test result. So you will only do the fine tuning of these parameters only checking at the result on the validation set, right? And generally, the data distribution should be same across this three data set, and at least your validation and test data distribution should be very similar, right? If until and unless if it is like very different in nature, you should not have that in your data set. Your validation and test should be a very similar type of distribution which you need to have, right? And the percentage which I mentioned, right? Like 70% is training data set, 20% is test, and 10% is validation, right? So this depends on the data volume on which you are working on, right? So in some of the cases, you might be having very small data set to work with, right? So that time you may need to like reduce the size of your test data set. There you can use a 10% uh, test and 10% validation, and 80% of them is like train. And so this all depends on the problem which you are working on, and also the volume of data which you have for doing the experimentation, right? And in some of the cases, you will see that it's a validation is not there. We are only working with train and test, which is fine, but it always has a risk associated with like the risk which we will talk in the next few slides, right? And this test and validation names are kind of used interchangeably, so don't get confused. Like if you see a different type of nomenclature, these two names are kind of used interchangeably, right? Now let's discuss few key concepts, which is like bias and variance, which is very essential for neural network because neural networks are quite susceptible to this bias and variance problems. Right now, let's try to understand with this few diagrams. Right, so we have this data set where like green cross are nothing but your data points of your training data set, right? And so you might be coming up with a neural network model which has certain characteristics, and after doing like several epochs, your model is kind of have a best fit line which looks like this, right? So here you can see your best fit line is not itself fitting to the line of data points of the training data set, right? So that we generally call as high bias, where your model is underperforming on the training data set, and the results are not good in the training data set itself, right? Then there is another kind of problem which we have. So here these are the same data points, and you have kind of trained the model in such a way that you have a best fit line where it's not a line anymore. It's kind of picking up every points in the data set, and it's trying to fit according to the training data set pattern, right? So it's quite sensitive to the training data set. And so in this case, we will see that this type of model will not perform well in case of test or validation data set, because this training was quite sensitive to the trained data set, and the model was not generalized well, and it will not perform well on the unseen data like test or validation. So here your model is performing well on the training data set, but it will not be performing well on an unseen data set like test or validation. Then there is another type, which is the line is like this, or the pattern of the best fit line or whatever curve you call, it looks like this. So it is not sensitive to your training data set, and the model is kind of generalized well to perform on the unseen data. So this is kind of a just right model which we are trying to build, and we are trying to find this sweet spot where your model is kind of just right, right? And if I just try to give you certain numbers, so these numbers are kind of representative in nature. These are not may not be the actual numbers. This is just to give you an example, right? So when our training set error is say 25% is the accuracy, right? So in that case, your model itself is not working on the training data set. So in that case, your the model, we will call that model is having a high bias, right? So in that case, it doesn't matter what it is performing on the validation data set, because it is not learning in the train set itself, right? Then there is the case of high variance, where your model is kind of performing well on the training data set, but it is performing poorly on the validation data set, right? So where the loss is kind of 20%, or the errors are 20% on the validation data set and 10% is on the um, training data set, right? So here, the 25% which I mentioned was accuracy. It's not accuracy, it's the error the model is making on the training data set, right? So yeah, and there is this just right model where your errors are like very close to each other while comparing with the training data set error and validation data set error, right? So you might be in either of these three cases. So if you are in the just right case, then you are very good to go with. But if you are having a high bias problem or a high variance problem, Let's see how to tackle that, right? Okay, so how we can achieve this? Just right state, right? So if you have a high bias problem, then these are the few solutions which you can try it out. You can have a bigger network where you increase the number of hidden layers, increase the number of nodes in each of the hidden layers. You try with more epochs, and you train longer, and like try to find out the results which are optimal in case of training data set, right? And you may go ahead and try different type of neural network architectures also, right? So basically, these are the three things which you can try out, like bigger network, more epochs, or training time. You can increase different neural network architecture to tackle with the high bias problem. Now, what about high variance problem, right? So in case of high variance, your model is not generalized well, right? It is very sensitive to training data set. So that's why you may need to feed more data into the model, and it will be generalized. You just hope that the model would be much more generalized using more data, right? You can make your model simpler, like you can reduce the number of hidden layers, you can reduce the number of nodes in each of the hidden layers. So with that, you will make your models much more simpler. And also you can use a concept of early stopping, or you can use certain regularization technique, like L2 regularization or dropout technique, which we will discuss very detail in the next few slides. So these are the techniques to tackle your high variance problem, right? So now let's go try to understand what this regularization is and how it solves the problem of overfitting, right? So generally we have this objective function where we try to find out the optimal values of W and B, weights and biases, so that your loss is, or the cost function is minimum, right? So this is kind of an objective function we try to find out, where for specific values of W and B, your cost function is, or the loss function is minimum, right? So what we do different in case of L2 regularization, right? So in case of L2 regularization, what we do is, apart from this regular function, we also add a term which is like lambda divided by 2m, and then we take the norm of W square, right? So this norm of W square is nothing but W transpose W, right? So we are just squaring each of the element wise weights, and then we are adding this term to the our cost function, right? And there is a separate type of regularization also, which is very similar to L2 regularization, but here we are, instead of squaring or taking the norm of W, we are just norm of W square, we are just taking the norm of W, right? And in this case, using L1 regularization, your W will be sparse. Lots of the weights will be zeroed out using this L1 regularization, and your model, as the few of the weights are getting zero, so your model will be much more simpler in nature, right? But in case of L2 regularization, what we do is we shrink the weight, and we try to shrink the weight, so that the model is kind of uh, more generalized, and the which will in turn reduce the overfitting problem, right? Now let's see how regularization helps in reducing the overfitting. So as I mentioned, like this is a formula which we use. So in case of weight updates, right? So in case of weight updates, what we generally do is uh, we take the derivative, and then using that derivative, we do the weight updates, right? And we calculate the derivatives, and we name it as DW, right? So in case of regularization, when you are using a regularization in the model, your DW would be a regular term, which is the gradient of loss function with respect to the weight. And then if you take the derivative of this part, the output will come as lambda by m multiplied by W. Right now, with this, if we try to do the weight optimization, you can replace W with this whole term, and you will see, if you just do the math here, you will see your W is getting multiplied with a term, which is like 1 minus learning rate times lambda divided by M, right? So this is getting subtracted. So this term is should be less than 1, because this term is getting subtracted from 1. So this would be less than 1, right? So now if you multiply W with a value which is less than 1, so your W will shrink and you will have an effect of weight decay. So your weights will be much more smaller, and as the weights are becoming much more smaller, your models will become less sensitive to your particular training data set, and you just hope that your model will be much more generalized in nature, right? And as we are shrinking the weight, or we are decaying the weight using this multiplicative factor of 1 minus learning rate time lambda by m, so that's why we call L2 regularization as a weight decay, right? As we are reducing the weight of our model weights, right? Yeah. So with that, the next concept, which also helps us to regularize our model, is dropout, right? So in case of dropout, what we do is we randomly select neurons or nodes which are ignored during training process. So we randomly drop out those nodes, and they do not contribute to the activation of downstream neurons which are temporarily removed from the forward pass or the forward propagation of while doing the training process, right? And we have associated weights for each of this dropout. Now this weight is nothing but p, which is a float value, which is nothing but a probability of an element to be zeroed, right? And in Pytorch the default value is 0.5. So it's like that each of the node has a probability of zero point 0.5 to be knocked out during the forward propagation, right? And they will not contribute to the backward propagation step also, right? I hope you got the concept. So here with this concept, you will see like these are the nodes which are like crossed out. So they will be dropped out during the training process, and they will not contributing while uh, doing the back propagation, right? And a few things to remember when using dropout, that dropout only is used during the training phase, and it is kind of switched off during the inference phase where we are doing the test or validation phase, right? And you should only use dropout when we have a overfitting that is going on in your neural network. Otherwise, if you use dropout, your model is not having a overfit, but if you still using dropout, you may run into the problem of high bias, right? Okay. Now the last concept in this video is early stopping. So in early stopping, what we have is if we plot our training and validation loss according to the epochs, right? So you will see that there would be a phase uh, where your validation and training loss is getting decreased, right? It's still decreasing till this point, and here you will see that training loss is still decreasing, but your validation loss is kind of started increasing, right? So it is going in a different directions. Both the loss are going in a different directions. So you may want to use a cutoff, and you want to stop your training process here, right? Because here you will get the optimal result, and here after that your validation loss is kind of getting increased. So you don't want to go to that path. So you may start your early stopping in this phase, where in this phase you have seen that your validation and training loss are kind of similar, and you will kind of monitor till this phase, and after this phase you will kind of stop training, right? You will not take any further you will not run any further epochs after this phase, and you will stop training. So with that, you will not run into the problem of overfitting, right? Because overfitting will be here, right? Where the gap between your validation and train is very large, right? So this is still okay, but this is where your validation is kind of diverting to a different path. And with that, we can stop here with this number of epochs, right? So these are the concepts which you should be familiarized with to tackle the problems of high variance or the high bias. So yeah, so that's all I have for this video. I hope you like this. So all the concepts which we discussed in this video, in the next video, we will try to see how to implement those in PyTorch. So yeah, with this, I will end this video. Thank you for your time. And if you like this video, please subscribe and like this channel. Thank you.